You've heard the line a million times. Just go faster, hit light speed, and the galaxy opens up. It sounds simple, like speed is the only thing holding you back. But the closer you push toward the speed of light, the less this looks like travel, and the more it looks like a slow, controlled way to destroy yourself, long before you reach any star. First, you need to understand the target you're chasing. Light in a vacuum moves at about 670 million miles per hour, around 1.08 billion kilometers per hour. That's so far beyond everyday speed that your normal sense of fast stops being useful. At that scale, tiny delays, tiny steering errors, and tiny pieces of matter all stop being harmless details. Every small thing is amplified by your speed into something that can kill the ship, or kill whatever the ship hits. In regular low-speed physics, you learn that kinetic energy goes up with the square of speed. That already means each extra mile per hour hits harder than the last. But near light speed, that simple rule is not enough. A new effect from Einstein's special relativity takes over, something called the gamma factor. You can think of gamma as a number that tells you how much the laws of physics are being bent by your speed. At car or airplane speed, gamma is basically 1, so you never notice it. As you go faster, gamma slowly climbs, and once you start getting close to light speed, it climbs very fast. So how bad does it get when you try to ride that curve? At 90% of light speed, gamma is already a bit more than 2. That means your moving ship behaves as if it has more than double its usual energy and inertia. At 99.9% of light speed, gamma is around 22. Now your ship is carrying more than 20 times its own rest energy in motion alone. Each tiny push closer to light speed costs a huge amount of extra energy. The curve gets steeper and steeper, and as you try to get all the way to light speed, that required energy blows up without limit. That is the deeper meaning of nothing can go faster than light. It is not just a rule someone decided, it is the universe telling you that trying to hit that speed demands energy you cannot realistically supply. Here's the problem though, you do not need to actually reach light speed before everything becomes dangerous. Long before that point, you have already turned your ship into something that carries absurd weapon scale energy. Take a ship that is not even huge by interstellar standards, say 1,000 tons, around 2 million pounds, about 900,000 kilograms, including engines, structure, shielding and life support. Push that to around 90% of light speed, and the kinetic energy locked into that motion is on the order of 10 to the 23rd joules. You do not need the exact figure, just the comparison, that is tens of millions of megatons of TNT. That kind of energy is not just a big explosion, that is the kind of energy that can strip the surface off a planet, or rewrite a whole planetary system if it is released in the wrong place. So now ask yourself, what does it mean to fly something like that through space? A software bug, a navigation mistake, or a failed sensor does not just risk one crew. It means the ship itself is now an artificial asteroid impact, with more energy than most natural impacts in the history of a planet. Your starship is not just transport anymore. By the time it is close to light speed, it is by definition a potential doomsday weapon. Then there is the environment you are trying to cross. People like to say space is empty, but that is only true compared to air or water. The average space between stars in our region of the galaxy holds roughly 0.1 to 1 atom in every cubic centimetre, which is 1 million particles in every cubic metre. At walking speed, that might as well be nothing. At the speed you are chasing, it is not nothing at all. So ask this, what happens when you slam into that almost nothing at a huge fraction of light speed? Think about the rate at which your ship hits those particles. At a large fraction of light speed, you are crossing huge distances every second, and every atom of hydrogen in your path hits the front of your ship at that extreme relative speed. In your ship's frame, those single atoms act like high-energy projectiles. They smash into your hull, dump energy, and turn into bursts of radiation and plasma. You're not drifting through a calm, clean vacuum. You're ramming into a thin but relentless gas that behaves like a continuous high-energy storm focused on the front of your ship. That leads to another key point. Once you start pushing toward light speed, you are not just moving through the universe faster, you are changing how the universe interacts with you. Time for you on board slows down compared to people back home. Distances along your direction of travel shrink from your point of view. The energy of every particle and every photon you meet is boosted by your motion. The faster you go, the more the background environment, the quiet space that looks harmless at low speed, turns hostile. So instead of a clean story where you just go faster and reach the stars, the real story is that chasing light speed bends every part of physics against you at once: energy, time, space, and matter. The engine that pushes you forward needs more and more power. The kinetic energy you carry turns your ship into a potential extinction-level weapon. The thin gas between the stars becomes a source of radiation and erosion, and the very structure of time and distance changes in a way that complicates everything from communication to navigation. This raises a hard question you cannot dodge if you take the science seriously. If the basic act of getting close to light speed already makes your ship act like a loaded weapon and turns empty space into a danger zone, what happens when you start adding up the actual energy bill required to reach those speeds in the first place? Because when you finally look at how much power you would need, how much fuel you would have to carry, and what that fuel actually is, the picture gets even worse, and the line between starship engine and planet killer almost disappears. If the speed itself is already a problem, what happens when you look at the power you need to get there and to slow down again? The answer is simple and ugly. You're not just building a fast ship, you're building an object that handles more energy than many stars push out in a second. Energy stops being a neutral tool. At this scale, energy is the main threat. So let's talk about a real ship, not a tiny probe or a cartoon rocket. Say you build a modest interstellar craft, around 10,000 tons, about 20 million pounds, roughly 9 million kilograms. That has to cover everything: structure, engines, fuel tanks, shielding, life support, crew habitat. Now you want to push that bulk up to 90% of light speed. The energy bill for just the motion, not counting losses, not counting slowing down later, is around 10 to the 24th joules. In plain language, that's a number with 24 zeros after it. It's comparable to a few percent of the sun's total output in a single second, focused into one ship. And remember, you don't pay this once. If you ever want to stop at your destination instead of just flying past it forever, you need another chunk of energy of the same order to slow down. So here's the next problem. How do you even deliver that kind of energy to a ship without turning the delivery system into a bigger nightmare than the trip? Rockets in the normal sense start looking ridiculous. Chemical rockets, the kind we use now, are instantly useless at these scales. Even nuclear fission or fusion, which release far more energy per pound than chemistry, start to struggle when you stack them against 10 to the 24th joules. That's why people jump straight to the most extreme option we know, matter-antimatter, where you convert almost all of the mass into pure energy. Now ask the hard question: even if you had almost perfect matter-antimatter conversion, how much fuel are you really talking about? Using that mass-energy rule to get 10 to the 24th joules, you're talking about thousands of tons of fuel, millions of kilograms annihilated over the course of your acceleration and deceleration. And that's in the ideal case, with no waste, no losses, no bad engineering. In reality, you'd need more. But forget the exact number for a second and just focus on this. Right now, on Earth, handling even a few ounces of antimatter would make a facility insanely dangerous. A containment failure gives you an explosion bigger than most nuclear weapons. Your starship needs to treat thousands of tons of that kind of material as routine consumable fuel. By the time you have enough high-energy fuel on board to do the mission, you've made your ship into a flying bomb before it even leaves orbit. But even if you somehow trust yourself with that much fuel, there's another basic question. What happens to the energy that does not go into speeding the ship up? No engine is perfect. Say you've done something miraculous and built a drive that is 99.9% efficient. That leftover 0.1% sounds tiny, but when you're dealing with 10 to the 24th joules, 0.1% is still 10 to the 21st joules that show up as waste heat. Spread over your burn time, that is still a crazy power level you have to get rid of. In space, you don't have air or water to carry heat away. You only have radiation, you glow infrared into the cold background. The only way to dump more heat is to make your radiators hotter or bigger, or both. So now your ship needs huge radiating surfaces running at thousands of degrees Fahrenheit, over 1,000 degrees Celsius, just to stop the inside from cooking. Those radiators are bright, hot and fragile. If they underperform, the heat backs up into the rest of the ship, electronics start failing, materials weaken, and crews overheat. The drive that looks elegant on paper starts acting like a slow cooker that your entire ship is trapped inside. So how does this compare to the power systems we actually know how to build today? Right now, some of the most power-hungry machines on Earth, like the Large Hadron Collider, pull about 1 gigawatt of power, roughly the output of a big power plant. The entire human civilization runs at something like 20 terawatts, 20 trillion watts, spread across the whole planet. To push a 10,000-ton starship up to 90% of light speed in anything like a human timescale, not millions of years, you're talking about continuous power levels many orders of magnitude above that. You'd need more power than our entire civilization uses, and you'd need it focused on one vehicle for long periods with extreme reliability. That means a light-speed capable ship is not just a spacecraft, it's a civilization-level infrastructure project. You either build gigantic power stations in space, maybe around stars, or you turn your ship itself into a compact, high-output power system that dwarfs anything humanity has ever made. In both cases, you're working with power levels where any mistake is catastrophic. A misaligned beam, an uncontrolled reaction, a containment breach. These aren't failures, they're extinction events. And here's the punchline that people don't like to think about. At these scales, there's no meaningful line between engine and weapon. The energy you need to push your starship to a large fraction of light speed and then slow it back down is the same kind of energy you would need to vaporize worlds. The same reactor that drives your ship can, if mishandled or attacked, become a bomb. The same antimatter tanks that promise efficient propulsion become instant doomsday devices if they crack. The same beam that pushes your ship with light sails could, if misaimed, fry surfaces on planets. So before you ever hit the throttle, before you ever leave your home system, you've already built something with the destructive potential of a small star. You're betting that nothing goes wrong, no one makes a bad decision, no system degrades, no one uses it on purpose as a weapon. And that's all before you add one more problem. Once you've spent all that energy and finally got your ship moving, it has to fly through a universe that is not empty. A universe full of dust and grit and random particles that, at those speeds, start behaving less like dust and more like constant nuclear level impacts. Here's the part most sci-fi stories skip. At near light speed, the smallest things in space become the biggest threats. Not planets, not stars, just dust. Stuff you would never notice at normal speed suddenly has enough punch to end your mission in a fraction of a second. Think about what dust means in everyday life. On Earth, dust is just annoying. It clogs filters, it scratches surfaces, you wipe it off and move on. Even in orbit, tiny paint chips or grains of sand are mostly a maintenance problem, not an automatic kill shot. But once you push your ship up to a large fraction of light speed, that same dust jumps from nuisance to lethal. The numbers behind that jump are brutal. Start with one tiny piece, a single grain of dust weighing about 1 milligram, that is 1,000th of a gram. To you, that is basically nothing, smaller than a crumb. Now give your ship a speed of about 90% of light speed. In your frame of reference, that little grain has an insane amount of kinetic energy. It is on the order of 10 to the power of 11 joules, which is roughly the energy of 30 tons of TNT. You're taking something the size of a speck and tying it to the energy of a small truckload of explosives. At that point, you don't get a dent. That grain slams into your forward shield, dumps its energy in a tiny area, and instantly vaporizes itself and a chunk of whatever it hits. The impact region turns into a superheated plasma, a spray of charged particles and high-energy photons. A shockwave travels through the structure, just like a pressure wave in a building hit by a blast. Even if the hull is not ripped open right away, internal components behind the impact zone can crack, joints can fail, people can be thrown into walls. And that's from one invisible speck you never saw coming. So maybe you think, fine, that sounds bad, but how often do you actually hit something like that? Way out between the stars? Isn't interstellar space basically empty? This is where the data hurts, because astronomers have already measured what is out there. When we look at stars in our galaxy, we see that some regions are dimmer and redder than they should be. That dimming, called extinction, is caused by dust blocking and scattering starlight. We also see thick dust lanes cutting across the Milky Way in telescope images. That's not theory, that's mapped structure. In the local interstellar medium, the space around our solar system, you're dealing with gas and dust densities that sound tiny, but add up over long distances. There are atoms, molecules, and solid grains ranging from microscopic sizes up to millimetre and larger. Over 1 light year, over 10 light years, the probability of your path crossing, at least some grains big enough to matter, is not tiny. It's basically guaranteed unless you take extreme precautions. You're not threading a perfectly clean vacuum, you are flying through a very thin but real fog of material that has been there for billions of years. So what do you do about it? Just put more metal in front of you and hope it's enough? That's the first instinct. Build a big heavy shield and let it take the hits. We already use layered Whipple shields on satellites in the space station. At orbital speeds of around 17,000 miles per hour, about 27,000 kilometers per hour, they work well. A thin outer layer breaks up the incoming grain. The inner layers absorb the spread out impact. But at 90% of light speed, the energy per grain is so high that these familiar tricks fall apart. When a high-speed grain hits solid armour at those velocities, the front surface doesn't just chip, it explodes. A chunk of the armour turns into plasma and high-velocity fragments. All that material has to go somewhere, and some of it will spray into the rest of your shield and potentially into the interior. To have any hope of stopping multiple hits from milligram-scale grains, you start talking about shields that are many feet thick, meters thick, made of dense material covering the entire forward cross-section of the ship. That adds massive weight, which demands even more energy to accelerate, which makes every impact even more destructive. It's a feedback loop that never really ends in your favour. If brute force armour can't solve it cleanly, what about being smarter? Can you just dodge the worst grains before they hit? In theory, you could set up powerful radar, lidar, optical sensors, and maybe magnetic detectors, scan the space in front of you, and use lasers or fields to vaporize or push aside incoming dust. It sounds clever, but relativity wrecks your timing. At around 90% of light speed, you cover about 100 million miles, around 160 million kilometers, in 15 minutes. That's more than the distance from Earth to the Sun in under a day of travel. A grain of dust 1 millimeter across is incredibly hard to spot at long range, even with perfect optics. By the time your sensors can see it clearly, you're already almost on top of it. Light takes time to reach you, your computers take time to process the signal, your defenses take time to respond. All of those delays eat into your reaction window. Instead of having minutes to decide what to do, you have milliseconds or less, and that assumes flawless systems running at the edge of what physics allows. You can try to extend the detection range with bigger telescopes or more sensitive arrays, but the basic limit is hard to escape. You're chasing light, and information about the hazard also moves at light speed. When you move too close to that limit, you leave yourself almost no margin. A single missed grain, a single sensor glitch, and the system that was supposed to protect you becomes irrelevant in the moment you actually need it. And here's the part that makes all of this even worse. Even when you survive an impact, you still pay a price every time. Each collision at relativistic speed, even with a tiny grain, sets off a shower of secondary particles and high-energy photons. You get bursts of X-rays, gamma rays, electrons and other particles punching into the ship. The shield takes structural damage, but the crew and electronics take radiation damage. Over years of travel, it's not just about one big hit that kills you outright. It's about constant micro-events, each one like a tiny nuclear explosion right on your hull, adding a bit more stress, a bit more erosion, a bit more cumulative radiation dose. Circuits fail early, materials become brittle, cancer risk for the crew goes through the roof, your protective shield slowly gets eaten away, and the environment around the ship becomes a mix of hot plasma, debris, and electromagnetic noise. So dust, something you never think about at airplane speed, turns into a stacked set of failure modes at near light speed. Structure, sensors, shielding, and biology all get hit at once, and this is just from solid particles. You still haven't dealt with the fact that even the soft background glow of the universe, the radiation that is harmless when you sit still, starts to blue shift and beam straight into your face when you push your speed this high. If dust can act like a line of hidden explosives in your path, what happens when every photon in front of you starts acting like a weapon too? You've already seen how dust becomes deadly when you go fast, but there's another problem that's even harder to escape. You can't turn off the light in the universe. Even if there were no planets, no asteroids, no dust at all, there would still be radiation everywhere. And the moment you push toward light speed, you crank that background glow up into something that looks a lot more like a weapon than a soft cosmic height light. Start with the quietest thing, the cosmic microwave background. Right now, sitting still in space, the universe is filled with a very cold, very weak glow. At about 2.7 degrees above absolute zero, that's 2.7 Kelvin. It's mostly microwaves, very low energy photons, too weak to worry about. You don't feel it, you don't see it. It just exists as a kind of fossil light from the Big Bang. But here's the catch. When you start moving at a big fraction of light speed, that glow does not stay soft and harmless from your point of view. Because of the Doppler effect, the light in front of you gets squeezed. The waves that used to be long and gentle get shoved closer together. Shorter wavelength means higher energy. The faster you go, the more the light in front of you gets pushed from microwave to infrared to visible to ultraviolet to X-ray, and eventually into gamma rays if your speed is extreme enough. That calm background you could ignore while sitting still turns into a sea of high-energy photons in your direction of travel. You've effectively turned the entire universe into a radiation bath, and you are the one flying into it on purpose. And that's just the leftover glow from the early universe. What happens when you add normal stars into the mix, the bright points you see in the sky right now? Light from stars ahead of you doesn't just shift in colour, it also piles up in intensity. As your speed climbs and your relativistic gamma factor gets larger, the light from in front of you becomes both more energetic and more concentrated. Visible starlight that would normally be safe for your eyes gets pushed into ultraviolet and X-ray. The overall brightness in your forward direction doesn't just double, it scales up very fast, roughly like gamma times gamma again, so every jump in speed hits you twice, in energy per photon and in number of photons per second. That means that even ordinary stars, the kind that would be totally harmless from a distance at rest, now start to behave like sources of intense radiation when you race toward them at relativistic speeds. Your forward face is under constant bombardment, not by some exotic weapon, but by regular starlight that your motion has turned aggressive. It's like you've taken the whole night sky and told it to shine straight into your shields at maximum power, non-stop. Now add one more relativity effect that really stacks the deck against you, aberration, also called relativistic beaming. When you move slowly, light comes at you from all directions. You see stars around you in a full ski. When you move close to light speed, the geometry shifts in your frame. Most of the light that was spread around your view gets squashed into a narrower cone in front of you. The universe visually pushes itself forward. It's not that the stars moved, it's that your high-speed motion changes how their light hits you. So instead of a gentle glow from all sides, you get a concentrated, forward-facing cone of radiation. All the danger gets focused where your ship is pointed. Forward becomes the worst possible direction to look, and unfortunately forward is exactly where you need to point your nose if you want to go anywhere. There is no safe orientation where you travel fast and avoid the beam, because the faster you go, the tighter and more intense that forward cone becomes. You've basically built yourself a scenario where every extra bit of speed makes the universe hit you even harder, right where your ship is leading. So how do you fight that? How do you keep that radiation from just cooking everything on board? For low-energy light, you can use thin metal, plastic, or special coatings. But once you're dealing with X-rays and gamma rays, you need real shielding, dense materials like lead, thick layers of water, or advanced composites designed to soak up high-energy photons. At the kinds of flux you'd see at extreme speeds, you're not talking about a thin panel, you're talking about shields that are several feet thick, several yards thick, across your whole forward area. That kind of shielding adds a massive amount of weight, which means more mass to accelerate, which means more energy you need from your engines, and more energy that can turn against you in an accident. And it still isn't perfect. Some gamma rays will always punch through, and when they hit dense material, they can generate more particles and more photons. Now picture what happens if that shield gets damaged, even slightly, by dust or micrometeoroids or structural fatigue. The moment you open a weak spot, that concentrated radiation from the forward cone has a direct channel into your ship. The dose rate inside can spike from manageable with careful design to lethal very fast. Even when your shielding holds, it doesn't just quietly absorb everything. High-energy photons hitting dense material create cascades, chains of new particles. A gamma ray slams into an atomic nucleus, kicks out electrons, maybe produces an electron and its antimatter partner, a positron. Those secondary particles fly off, hit other atoms, release more photons, and the shower spreads. That's why high-energy radiation is so hard to contain. It doesn't just stop, it branches. Inside your ship, that means any area behind the forward shield lives in a constant drizzle of ionizing radiation. Particles and photons energetic enough to break DNA, damage cells and cause long-term health effects. Electronics are also sensitive. High-energy hits flip bits in memory, break down semiconductors, and slowly kill circuits. You need hardened systems, redundancy, and constant monitoring just to stay ahead of the damage. And all that absorbed radiation energy turns into heat, adding to the cooling problem you already have from the engines and from particle impacts. So when you think about near light speed travel, don't picture a ship gliding through cold, empty darkness. What you really have is a vehicle ramming into a forward cone of boosted light, microwave background pushed up toward X-rays, starlight shoved into higher energies, all of it beamed into your face by relativistic geometry. Your shields are not just armour, they are the front plate of a nuclear reactor, taking hits from everything the universe can throw at you every second you stay at that speed. And this is still only the radiation that started as light. Once you remember that space is also filled with high-energy particles, cosmic rays that already hit Earth's atmosphere with more energy than anything our colliders can make, you hit the next level of trouble. Because when you go near light speed, you don't just boost photons, you boost those particles too, and then your ship stops being just a target in a radiation furnace and starts acting like a human-sized particle accelerator, slamming storms of extreme particles straight into your hull. You'd think the worst radiation problem on a near light speed ship would be the stuff you generate yourself, from engines and hot shields. The uncomfortable truth is, the universe is all rare full of bullets, and when you go fast enough, you help those bullets hit harder. You turn your starship into the worst place to be in a cosmic ray storm, because by going that fast, you're effectively cranking that storm up yourself. Start with what cosmic rays are right at now, before you move at all. Space is full of high-energy particles, mostly protons and atomic nuclei, flying in from all directions. We've measured some of them hitting Earth's atmosphere with energies far beyond anything our biggest machines can produce. We're talking about single particles carrying as much energy as a hard-thrown baseball, but packed into something smaller than an atom. Our best collider, the Large Hadron Collider, can accelerate particles to incredible energies, but these natural cosmic rays go tens of millions of times beyond that top end. When they slam into the upper atmosphere, they trigger huge particle showers, spraying secondary particles down toward the ground. Most of those are absorbed before they reach you thanks to the thick air column above your head. Now ask what happens when you're not sitting safely at the bottom of an atmosphere, but riding in a metal shell in deep space and you decide to go to say 90% of light speed. Those same cosmic rays are still out there, coming from all directions, but from your frame of reference, the ones coming from ahead don't just look energetic, they look dramatically more energetic because of relativity. Your motion boosts their energy, just like it boosted the energy of photons in the forward direction. That high-energy proton that was already bad news in normal space now looks like an ultra-extreme projectile, far beyond what we deal with on Earth. In effect, your hull becomes the atmosphere. Instead of those particles slamming into miles of air, they slam into a few inches or a few feet of metal and composite. All the complex particle showers that used to unfold high above Earth's surface now unfold right on your ship's skin. That's a huge difference. On Earth, we get the diluted, filtered version by the time the cascade is done. On your ship, you're sitting right next to the splash zone. This is where your starship starts acting like a human-sized particle accelerator experiment that never shuts off. A single ultra-energetic cosmic ray proton hits your hull. It smashes into a nucleus in the material, and instead of just stopping, it explodes that nucleus into a shower of new particles, pions, muons, electrons, gamma rays, and more. On Earth, we build giant underground detectors to catch these showers and measure their properties. On your ship, every hit like that is essentially a tiny high-energy physics experiment happening right next to your crew quarters, your computers, your life support systems. And this isn't a rare event that happens once a year. At relativistic speeds, the flux of cosmic rays from the forward direction is boosted. You get more of them, and each one hits harder. Over months and years of flight, you are constantly exposed to these showers. Even if the hull never cracks, the interior is being peppered by bursts of ionizing radiation every time one of those cascades brews up just outside. You might think, fine, just make the hull thicker, add more shielding, problem solved. But here's the hard part. Even if you stop the initial cosmic ray, you haven't really deleted the danger. The shower it triggered doesn't just vanish. The secondary particles can be neutral or only weakly interacting, and they can penetrate deep into the ship. Neutrons are especially ugly. They carry no electric charge, so magnetic fields don't deflect them, and they can travel a long way into metal, plastic, and human tissue before they finally interact. When they do interact, they hit nuclei and can make them radioactive or dump energy straight into cells. For humans, that means raised cancer risk, damage to bone marrow, increased chance of acute radiation sickness if the dose gets high enough. For the ship, it means electronics slowly getting fried as high-energy hits knock atoms out of place in semiconductor lattices, flip bits in memory, and slowly degrade components. You can try to put critical systems deep inside, behind extra shielding, but the more protection you add, the more mass you carry, and the more energy you need to get to speed in the first place. So now you're stuck between life support and particle physics. You need to keep your crew alive, which means keeping doses of ionizing radiation below certain thresholds over the whole mission. At the same time, the physical reality is that your speed is turning every cosmic ray head-on into a mini disaster. One obvious idea is to use powerful magnetic fields around the ship to deflect charged particles, bending their paths away from the hull. That's the same principle Earth's magnetic field uses to protect us from many solar and cosmic particles. But strong fields mean heavy coils, complex superconducting systems, more points of failure, and they only help with charged particles. Neutrons and high-energy photons don't care about your magnets, so you end up stacking solutions: thick physical shielding, magnetic fields, clever hull geometries, sacrificial layers, and hardened electronics. Every one of those steps costs mass, power, money, and complexity. Every fix adds something else that can break. And at the end of the day, you cannot make the exposure go to zero. At near light speed, the universe is constantly feeding your ship a diet of cosmic rays, boosted by your own motion, and your best realistic outcome is to push the risk down to maybe survivable over the mission length. This is the pattern that keeps showing up when you take lightspeed travel seriously. You push your speed up, and the normal background of the universe pushes back harder. Dust turns into explosive impacts. Gentle radiation turns into a forward cone of X-rays and gamma rays. Existing high-energy particles turn into something worse than anything we normally face, and your ship becomes the place where all of those effects overlap. And even if you somehow manage to keep the hull in one piece and the crew alive inside this storm, there's another problem waiting for you. The universe also punishes how fast you try to change your speed. Because to get up to those velocities, and to steer and stop again, you have to accelerate. And your body doesn't care how advanced your engine is, it only feels the force. You can build the shields, harden the electronics, stock the fuel, but what do you do when the thing that quietly kills your mission isn't a weapon or a storm, it's time itself? At near light speed, physics gives you a strange advantage. Your own clock slows down, you age less, you win against time. But the price is that everything you left behind runs away from you so fast that the mission, the context, and maybe your entire civilization stop lining up with your tool. Start with the basic effect. At about 99% of light speed, your relativistic factor, that gamma number, is around 7. That means, from Earth's point of view, your ship's time is running 7 times slower. If people on Earth watch you fly for 70 years, the clocks on board only tick through about 10 years. You live those 10 years normally, your heart rate is the same, your thoughts feel the same, your body ages like it's 10 years older. Then you step off the ship and everyone back home, if home even still exists, has aged 70. So in your personal time bubble, the trip felt long but manageable, like a tough assignment or a long deployment. But for the planet that launched you, this was a multi-generational event. Technology has moved on. In the extreme case, your homeworld might have gone through collapse or transformation so deep that you would barely recognize it. New languages, new cultures, new priorities. You survived the trip, that part worked. But the mission you thought you were on, the people you thought you were serving, might no longer be there in any meaningful way. That raises a sharp question. Does time dilation let you cheat the universe? Can you use that slowed clock to get ahead of events? To be there in time for something huge and distant? The answer is no, because you can't outrun causality. Say you see a supernova, a star blowing itself apart 10,000 light years away. The light from that explosion has been travelling for 10,000 years to reach your telescope. The event is already ancient by the time you even detect it. If you launch a near light speed ship toward that supernova, you're not racing the explosion, you're chasing its ghost. The matter has already blown out. The core has already collapsed, maybe into a neutron star or a black hole. Even if your ship experiences only a few years of onboard time during the trip, the rest of the universe doesn't rewind. By the time you arrive in the frame of that distant system, the event you cared about is long over. Time dilation helps you personally. It shortens the trip on your own clock, but it never reverses the order of cause and effect. Light still left that star first, then reached you, then you left. You can never get back in front of that chain. So what does that do to the fantasy of rapid response across interstellar distances? Think about sending a near light-speed rescue mission, or some kind of urgent delivery. Any problem worth responding to is already old by the time you hear about it, because the signal carrying the bad news also moves at light speed. A distress call from 10 light years away is already 10 years old when it reaches you. If you then send a ship at say 90% of light speed, maybe the crew feels like they arrive a few years after launch. But in the frame of the target, a lot more time has passed, decades at least. By the time you get there, the war is over. The disaster has either burned itself out or wiped everything clean. You show up as an echo from an earlier era, with orders and goals that make no sense anymore. On paper, you built the fastest possible response. In reality, you've built a system where timely response over those distances is basically impossible. Strategy collapses into slow motion because you can't send ships or messages that arrive before the situation changes radically. Now flip perspectives. Look at this from the point of view of the civilization that sends ships out. When you push vessels to relativistic speeds, you're not just sending them far away, you're sending them out of sync with your own timeline. From Earth, a mission may take 100 years, 200 years, more, before you ever hear from them again, if you hear at all. Any data they send back travels at light speed, so their status updates arrive decades or centuries after the fact. We already know that when we look at distant galaxies with telescopes, we're seeing them as they were billions of years ago, not as they are now. With relativistic travel, you create that effect inside your own story. Your ships, your outposts, your distant colonies become like those galaxies, delayed images, old versions of yourselves reaching back from the past. And from the crew's perspective, it's just as strange. They leave a world they know, they live through maybe 10 or 20 years of ship time, and when they check in, the home civilization has leaped forward in a way that feels disconnected, like trying to talk to someone who has skipped 5 seasons of your life. That feeds into something we don't talk about enough when we treat time dilation like a cool trick, the psychological side. Astronauts on the International Space Station already report isolation, stress, and mental strain after months in orbit, even though they can talk to Earth in almost real time, even though they return to a world that matches the one they left. Scale that up to relativistic travel. You sign up for a 5-year mission in your own frame, and you know going in that, depending on your speed and distance, 100, 200, maybe more years will pass back home. You come back technically home, but everything that defined home has been cut out from under you. Your family has gone many generations back. The culture you grew up in is a history topic. The music, the slang, even the basic technology may feel alien. You didn't just travel in space, you hopped over a huge chunk of your civilization's timeline. It's not just that you're older, it's that you're out of phase with everyone else. So yes, time dilation protects you from long trip boredom and aging in one sense. Your body and brain do less waiting for the same distance. But in exchange, it kills the original meaning of mission. You can't arrive in time to see events as they were when you launched. You can't maintain a tight, real-time relationship with the society that sent you. Every long-range relativistic trip turns you into a kind of time exile, physically alive but cut off from the context that made the journey seem worthwhile in the first place. And remember, all of this is stacked on top of the earlier problems, the energy bills, the dust impacts, the radiation, the cosmic rays. So now you're in a situation where even if you somehow solve the engineering, you still face a deeper question. What's the point of arriving alive if by the time you get there, the environment between the stars has been trying to kill your ship the whole way, and the universe itself has quietly erased the reason you launched? You've heard that space is empty, but if that were really true, you wouldn't have to worry about anything between the stars. The problem is, it's not actually empty, and at high enough speed, even a few lonely atoms here and there stop acting like nothing, and start acting like a thin, invisible atmosphere that never ends. Start with the actual numbers, because this part is measured, not guessed. The region around our solar system, the local interstellar medium, has roughly 0.1 to 1 particle in every cubic centimetre, mostly hydrogen atoms. That works out to about 1 million particles in every cubic metre. If you're walking or even flying in a jet, that may as well be perfect vacuum. There's no drag you can feel, no heating, no glow, but at around 90% of light speed, every single one of those atoms slams into the front of your ship with relativistic energy. Each one is now a tiny high-speed projectile, and you are ploughing through millions of them every second non-stop. So what does that actually do to your ship? The key idea is ram pressure, the effective push of the medium you're moving through. Ram pressure scales with the density of the stuff you're hitting, and with the square of your speed. Double the speed, 4 times the ram pressure. Multiply the speed by 1,000, and that pressure goes up by 1,000,000. Once your velocity is a serious fraction of light, that tiny background gas becomes a real force. In front of your ship, the gas can't get out of the way instantly. It piles up, gets compressed, and heats up. That's where you get a bow shock, a region in front of your ship where the interstellar gas is forced to slow down and change direction in your frame. Compression and friction at that shock heat the gas to extreme temperatures, turning it into plasma, a soup of ions and electrons. That hot plasma then slams into your forward shield, adding mechanical stress and radiation on top of everything the dust and photons are already doing. You're not just in empty space anymore, you've created your own moving shock front, and you crash into it every moment you're at speed. To get a feel for how nasty this can get, think about something we already know: atmospheric re-entry. When a capsule comes back into Earth's atmosphere at around 17,000 miles per hour, about 27,000 kilometers per hour, the air in front of it gets compressed and heated to a plasma that can reach around 4,000 degrees Fahrenheit and about 2,000 to 200 degrees Celsius. That's why you need heat shields, lative tiles, careful trajectories, but that's for just a few minutes during re-entry. A relativistic starship is doing a version of that, not for minutes, but for years, through a very thin but still real interstellar gas. So now your forward face isn't just a shield, it's a surface that's constantly being hammered by hot plasma, high-energy ions and radiation, mile after mile, light year after light year. There's no break, no, we're through the atmosphere now because this invisible atmosphere stretches between every star you want to visit. You've basically signed up for permanent re-entry without the option to just slow down and coast. On top of the heating and shock, there's another slower but deadly effect: erosion. When high-energy ions hit a solid surface, they knock atoms out of it in a process called sputtering. At low speeds, sputtering is already a headache. We've seen it on satellites and space station hardware in low Earth orbit. Micrometeoroids and reactive atomic oxygen have chewed away at coatings, surfaces and thin films over time, even at only orbital speeds. Engineers have had to redesign materials and protective layers because of this. Now take that same sputtering effect and scale the speeds up by factors of thousands or millions. Each ion, each atom that hits your hull at near light speed, has far more energy and is much more effective at knocking atoms loose. Over years of operation, your forward shielding physically wears away. The outer layers get rough, pitted, thinner. Microscopic damage can turn into cracks. Coatings designed to reflect or absorb radiation degrade. If you don't constantly maintain or reinforce the shield, you risk reaching a point where it's simply not thick enough to do its job. And there's still another twist. The gas you're ploughing into isn't just dead weight. It can actually power more trouble. As the interstellar medium gets compressed and heated in front of you, the electrons and ions in that plasma are moving through your ship's magnetic field and any fields generated by your engines and shields. Charged particles moving in magnetic fields don't go straight, they spiral. When they spiral, they emit radiation, known as synchrotron radiation. They also radiate when they slow down or change direction in electric fields, called Bremsstrahlung. So now you have a loop, your ship's speed creates a shock, the shock makes plasma, the plasma particles spiral in fields and throw off high-energy photons, which then slam back into your shield and your surrounding environment. That radiation in turn heats things more, knocks loose more particles, and can destabilize the plasma flow. You can get complex electromagnetic instabilities, waves and fluctuations in the plasma that feed off the energy you're pumping into it. The background medium, which started as a sparse gas you thought you could ignore, becomes an active, noisy radiation-producing system attached to the front of your ship. All of that adds to your engineering headache. You're now dealing with mechanical stress on the hull from ram pressure, thermal stress from heating, material loss from sputtering, and radiation from both the shock and the instabilities in the plasma. The vacuum you thought would be your ally is now throwing everything it has at your bow, all because you insisted on moving through it at extreme speed. And this is the pattern you keep running into at near light speed. Every background effect you used to round down to zero, gas, dust, photons, cosmic rays, suddenly rounds up to serious problem just because you chose to move fast. The interstellar medium doesn't just sit there, it reacts. It heats, it glows, it erodes your hardware, and it sets up electric and magnetic fields that can interfere with your systems, which leads straight into the next issue. Once you wrap your ship in a cocoon of hot, magnetized plasma, you're not just dealing with heat and erosion anymore, you're flying inside your own electromagnetic storm, and that storm would really like to kill your electronics before you ever see another star. You've already turned the space in front of your ship into hot plasma, so the next question is, what happens when that plasma starts hitting back, not just with heat, but with electricity and magnetism too? At near light speed, you're not only dealing with collisions, you're flying inside a mess of electric fields, magnetic fields and radiation that your own motion created. We already see a mild version of this with things we understand today. Meteors hit Earth's atmosphere at tens of thousands of miles per hour. They ionize the air, they leave glowing plasma trails. Spacecraft on re-entry generate plasma sheaths that block radio signals for minutes. Those speeds are nothing compared to a relativistic starship, but the physics is the same type, just cranked up. When your ship slams through the interstellar medium at a big fraction of light speed, you don't just heat up the gas right at the hull. You ionize and shock the gas far ahead of you. You carve out a region of compressed, charged particles that wrap around your bow and trail behind you. That region is not neutral, it's made of electrons and ions separated and moving at different speeds, so it carries currents and builds electric fields. As they move, those charges generate magnetic fields. You end up surrounded by layers of plasma, with strong electric and magnetic fields changing in time as the flow shifts, as your orientation changes, as density bumps in the interstellar medium come and go. You've basically wrapped your ship in a moving electromagnetic environment that is constantly shifting, because your own motion through the gas keeps pumping energy into it. Now ask what those changing fields do to a big metal object full of wires, circuits, and antennas. Basic electromagnetism says that changing magnetic fields induce currents and conductors. That's how generators work. It's also how a solar storm 93 million miles, about 150 million kilometers away, can induce currents in power lines on Earth and damage transformers. We already worry about that, and that's from a star you're not even moving toward at high speed. Your ship, at relativistic speed, is not waiting for a storm. It is flying straight into one it created. As the plasma around you shifts and the magnetic fields fluctuate, they drive currents in your hull, in structural supports, in cable runs, in antenna booms. Sudden spikes in those fields translate into surges of current, which dump energy into components that were never meant to handle it. You can get unwanted voltages appearing across connectors, sparks across small gaps, and overloads in sensitive electronics. It's like having a constantly changing, invisible induction coil wrapped around your vehicle, hitting random parts of your electrical system. On Earth, we install surge protectors and grid-level hardware to handle rare, strong events. On a relativistic starship, you would need that level of protection running all the time, everywhere. And the plasma itself is not quiet in terms of radiation. Electrons moving through magnetic fields don't just spiral. While they spiral, they radiate energy. That's synchrotron radiation. Electrons slowing down or changing direction in electric fields radiate too. That's Bremsstrahlung. We see both of these in space already. They power the bright radio lobes of galaxies, the X-ray jets coming from around black holes, and the emissions from supernova remnants. Those objects are huge, but the fundamental processes are the same ones you're now triggering on a smaller scale in front of your ship. So your bow shock and plasma sheath become a source of broadband electromagnetic radiation, from radio waves all the way up to X-rays, depending on how extreme your conditions are. Some of that radiation goes forward, some sideways, some back onto your own hull. Your ship, in other words, stops being just a passive object moving through space and starts being an active emitter, a little version of the violent astrophysical systems we see through telescopes. And that extra radiation adds to the heating, to the ionizing dose, and to the background noise your electronics have to live in. That brings up a practical problem. If your own motion is generating this much electromagnetic noise, how do you talk to anyone? Any radio signal you try to send from inside this plasma bubble has to pass through a layer of charged, turbulent gas before it reaches open space. Plasma can reflect, absorb, and scatter radio waves, especially at lower frequencies. It can bend beams, add delay, and create fast fluctuations in certain signal strength. On re-entry, spacecraft lose contact for a short time because of a much weaker plasma sheath at much lower speed. You're dealing with a stronger, more complex version of that, not for minutes, but for as long as you cruise at relativistic velocity. You might switch to tightly focused, high-frequency beams, like narrow laser communication systems, to punch through some of the interference. That helps, but it doesn't completely solve the problem. the plasma can still distort the beam slightly, and any jitter in your ship's orientation feeds straight into pointing errors. On top of that, the electromagnetic noise from your own bow shock raises the floor of background signal around you, making it harder for sensitive receivers to pick out faint incoming transmissions. You're trying to beam a clean message across light years while sitting inside a moving cloud of static. Now look at how all these pieces tie together as you increase the speed. Go faster, and the ram pressure goes up. That makes the bow shock stronger. A stronger shock raises the plasma temperature. Hotter plasma means more energetic electrons and ions, which radiate more strongly when they move through fields. More radiation and stronger fields mean bigger induced currents, harsher conditions for electronics, more ionizing exposure for the crew, and more heating of the shield. If any of that damages the structures or systems that shape your fields, the plasma can become even more unstable, which feeds back into the fields again. This is the feedback loop you run into. Faster speed leads to stronger shock leads to hotter plasma leads to more radiation and more electromagnetic chaos, and that chaos leads to more damage and higher failure risk. It's not just that you have lots of separate problems. At near light speed, fluid dynamics, plasma physics, high energy radiation, and electronic reliability all get tied into one big interlocked failure mode. A small issue in one area can cascade into trouble in all the others. So you're not just designing a fast ship, you're designing something that has to stay stable while it drags a self-generated high-energy plasma environment around with it for years, with no brakes. And all of this is still before you deal with another basic fact. To get to these speeds, and to steer and stop again, you have to accelerate and turn, and that means subjecting your crew and your structure to forces that, if anything goes wrong, can turn the people inside into paste long before any external threat reaches them. How do you push a starship to a big fraction of light speed and not kill the crew before space even gets a chance to? You can solve the energy problem on paper, you can design shields and radiation protection, but every one of those plans has to pass the simplest test of all. Can human bodies actually survive the forces you need to apply to get the ship moving, turning and stopping? Start with what a person can realistically handle. On the ground, you live at 1 Earth gravity, about 32 feet per second, about 9.8 meters per second. Astronauts in launch and re-entry profiles can tolerate around 3 to 5 times Earth's gravity for a while, especially if they're lying in the right position and wearing special pressure suits. Fighter pilots in high-performance jets can hit around 9 times Earth's gravity in short bursts before blacking out, and that's already at the edge of what training and gear can manage. Those are minutes, not months, and they're carefully planned, not constant. So now ask the key question. If you want to reach around 90% of light speed without crushing the crew, how hard can you push, and for how long? If you pick a steady 1 Earth gravity acceleration, about 32 feet per second, about 9.8 meters per second, that's actually comfortable for humans. You just feel like you're standing on a floor. But you have to keep that up, not for a minute, but for roughly a year of ship time to get close to 90% of light speed, and then again in reverse to slow down at the destination. That means your engine has to deliver enormous constant thrust and power for that entire stretch with no major interruptions. Now, think about what happens if anything goes wrong during that long push. If thrust suddenly spikes, or the vectors shift sharply, the effective gravity the crew feels can jump. Double the acceleration for a bit, and you are at 2 times Earth's gravity. Triple it, and you are at 3 times Earth's gravity. These are not just numbers. 3 to 5 times Earth's gravity for long durations, blood circulation, breathing and organ function all start to strain. At 6 to 9 times Earth's gravity, people black out, blood drains from the brain, and internal tissues can actually shear if you maintain that level for too long. So your routine acceleration has to be incredibly smooth and controlled, because even short spikes can be dangerous. And that's just looking at the crew as if they were simple weights in a physics problem. Real ships are structures, not rigid blocks. 1 Earth gravity applied perfectly along the main axis is the best case. In reality, you have tanks of fuel that slosh, engines that gimbal, structural joints that flex slightly, and loads that shift. A long, slender starship under thrust can bend and vibrate, like a skyscraper in an earthquake or a long bridge in a storm. Except here, the earthquake is the acceleration you need to keep on for months. Every time the thrust direction changes slightly, or the internal mass distribution shifts, you get local areas of higher stress. Some beams are in compression, some in tension, some in twisting modes. Over months of continuous acceleration, those loads can cause metal fatigue, micro cracks, and structural creep. You have to design the ship not only to survive the peak force, but to take that force again and again without slowly tearing itself apart. And that's before you try any complicated maneuvers. Now picture you're at speed, you've spent all that energy and your ship is cruising at a large fraction of light speed when your sensors pick up a potential threat ahead, maybe a larger rock, a dense dust region, or another object in your path. You want to dodge, so you think, just turn a little. The problem is, at these speeds, even a small change in direction over a short time demands large lateral accelerations. Your velocity is huge, so changing the direction of that velocity fast means big side forces. From the crew's perspective, that feels like a sudden sideways gravity being switched on. Humans can tolerate a certain amount of straight-line acceleration if they are aligned with it and strapped in. Sideways forces are worse. At 6 to 9 times Earth's gravity sideways, people lose consciousness. Sustained high lateral forces can cause blood vessels in the brain and eyes to burst, organs to shift within the body cavity, and serious internal injury. So the maneuver you need to save the ship from an external hit can itself be deadly to the people inside, unless you spread it over a long time, which might not be an option if the danger is close. You can try to design the interior layout so that any expected acceleration is along the body axis of the crew, chairs turned to the right way, floors oriented with the thrust, but you can't guarantee that every unexpected event will line up with those plans. And if your navigation system ever decides it needs a sharp course correction, the conflict is immediate. Do you prioritize saving the hull or saving the people from the gravity load? At this point, science fiction usually throws in a cheat phrase: inertial dampers, artificial gravity, some device that soaks up inertia so the crew doesn't feel the acceleration. In real physics, there's nothing like that. You can't locally switch off inertia. When you accelerate, forces have to be transmitted through your body, through the ship, and through everything on board. You can spread the forces out more evenly with good engineering. You can use rotating sections to simulate gravity under some conditions, but you cannot make a 10 times Earth's gravity maneuver feel like 1 Earth gravity just by flipping a switch. The basic rule, force equals mass times acceleration, does not give you an escape clause. That means inertia itself becomes one more enemy on the list. The faster you want to go, and the quicker you want to turn or stop, the more dangerous the forces are to your crew and your structure. You can choose to accelerate gently, stretch your trip times and keep the load safe, but then you run into the time and mission problems we already talked about. Or you can push harder and shorten the trip, but then you have to accept that every accident, every emergency thrust change is a direct threat to human survival inside the ship. So even before dust hits you, before radiation builds up, before the interstellar medium erodes your shield, your own attempt to reach those speeds is putting the people on board right on the edge of their physical limits for months or years. And the more edgy your acceleration profile is, the more one fact starts to stand out. It doesn't matter how advanced your engine is or how strong your hull is, if your sensors and navigation can't see dangers in time, because at near light speed, you have almost no warning to adjust anything without crossing those lethal force limits. You can have the best engines, the thickest shields, and the toughest crew, but none of that matters if you can't see the threat soon enough to do anything about it. At near light speed, the real killer is not just what's out there, it's how late you find out about it. Start with a simple point that's easy to miss. Your sensors are limited by the same speed limit you are. Cameras, radar, lidar, whatever you use, they all rely on signals that move at or below the speed of light. If you are cruising at around 90% of the speed of light, and there's something sitting in front of you, The photons bouncing off that object and heading back to your detectors are only crawling ahead of you by that last 10%. They don't have a huge lead. By the time those photons make the trip from the object to your ship, you've already closed a lot of the distance. So think about what that really means. Every detection is delayed. You never see the current situation out in front of you. You see how it was a tiny fraction of a second ago. At slow speeds, that lag doesn't matter. At relativistic speeds, that lag is everything. If you're too close when you first pick up the signal, you are basically already on top of whatever you just discovered. The universe doesn't give you early warning, it gives you a late notification. Let's put some numbers on that reaction window to make it concrete. Suppose your detection systems are good enough to spot a large object at a distance of 1 light second, roughly 186,000 miles, about 300,000 kilometers. That sounds huge, farther than the distance from Earth to the Moon. At normal speeds, that's a generous amount of space to plan a maneuver. But if you're moving at 90% of light speed, you cover that 1 light second distance in just a bit more than 1 second of your own time. Now cram everything that needs to happen into that 1 second. The photons from the object travel to your ship, your sensors register them, your computers process the data, recognize a threat, choose a course correction, fire the thrusters, and then the ship's velocity vector actually changes enough to matter. All of that has to fit into that tiny window. Any delay in the chain, any hesitation, any extra processing step eats into time you simply do not have. That's not a safety margin, that's a coin flip, and that's assuming you even detect the object at a full light second in the first place. And that's for big targets. The dust and small rocks that can ruin your day are way harder to see. To spot tiny grains of dust or football-sized boulders at long distances, you need insanely high resolution at huge ranges. Even with powerful telescopes on Earth, working from a stable observatory, we struggle to detect small near-Earth asteroids at a few million miles away. They are dim, they blend into the background, and they move. We miss some. Now you're asking your ship to do better, on the fly, while moving at relativistic speed, with tight energy budgets, and in the middle of plasma and radiation noise. It's not just seeing the object, it's distinguishing it from everything else. Sensor glare, cosmic rays hitting detectors, reflections, instrument noise. Every false positive means wasted maneuvers or unnecessary stress on the system. Every false negative means a possible instant kill. You're balancing on a knife edge where the requirements for resolution, sensitivity, and speed are all pushed to extremes at the same time. That's a lot to ask from any hardware. Then there's the question of who or what is actually steering. Human reaction times are measured in tenths of a second. That's already too slow for high-speed fighter jets in some scenarios. Pilots rely heavily on automated systems. At near light speed, human reflexes are basically irrelevant for real-time navigation. By the time you see an alert, think about it, and decide what to do, you've already flown through the critical distance. So whether you like it or not, a relativistic ship has to be flown by fully autonomous control systems. That means you are trusting your life and this most expensive machine your civilization has ever built to software that is making decisions at relativistic stakes. It has to analyze sensor data, classify threats, predict trajectories, and fire thrusters or adjust fields without asking permission. It has to choose in real time between taking a hit and pulling a maneuver that might push the crew close to dangerous acceleration levels. And you have to be confident that it will not overreact to noise or underreact to real danger for years of continuous operation. And even if you solve all of that, you still run into the final problem: you can't see everything and you can't armor against everything. A single rock the size of a football at those speeds carries kinetic energy comparable to a large conventional bomb. It doesn't need to be an asteroid to wreck your ship. If that rock hits a weak point in your shield, or an area that has already been thinned by erosion, you can lose systems in one shot. It might not blow the ship completely apart, but it can kill key hardware, breach compartments, or trigger cascading failures. You can layer armor, use active defenses, run multiple sensor suites, and let smart systems steer, but the underlying facts don't change. you're moving so fast that information about the world in front of you reaches you with almost no lead time. The targets you need to worry about are small, dim, and sometimes effectively invisible until it is too late. And the energy of even a small collision is huge. The navigation problem stops being a matter of clever piloting and becomes something deeper. It's an existential limit on how safe you can ever make this kind of travel. So now stack that on top of everything else, the energy, the dust, the radiation, the plasma, the acceleration limits. You're trying to thread a needle at absurd speed using delayed information, with human bodies that can only tolerate so much force inside a machine that's already on the edge of what physics allows. And even if you somehow make it through all of that and reach another star, there's still another limit waiting for you, because your ship can't outrun the speed of light for communication either. You might arrive, but the story of what you did and why you did it will trail behind you so slowly that it almost doesn't matter. You can survive the trip, reach another star, and still lose the one thing the mission was supposed to deliver: information. If the whole point is to learn something and send it back, what happens when the universe stretches your messages so far in time that by the time they arrive, nobody is really listening? Start with the basic limit. Your ship cannot talk faster than light. A vessel sitting 10 light years away from Earth is, by definition, 10 years of light travel away. Even with a perfect laser transmitter, a perfect receiver, and zero noise, any message you send home takes 10 years to get there. That's the flaw. Now stack time dilation on top. Maybe your crew experiences only 3 or 4 years of onboard time before they reach that distance, but when they fire off a "we made it" message, Earth won't hear it until a decade after launch. If they send it later in their mission, the delay is even bigger. For the people on board, it feels like they're still in the middle of the story. For people back home, the story advances in long, slow jumps separated by many years. Once you accept that, remote control stops being realistic. You cannot sit in a control room on Earth, watch a live feed from a relativistic ship, and send commands like you do with a Mars rover. Any instruction you send arrives years late. By the time a turn-left command reaches the ship has already passed the point where turning left mattered. There is no way around that, so every high-speed interstellar mission is, by design, an almost one-way decision. You launch the ship, you program its guidance and goals, you allow some degree of autonomy, and from that point on you're not really steering. You're just waiting to hear what happened long after the fact. That also changes how you think about what the ship sends back. On a science mission, you do not only want pretty pictures, you want data stake, as well as data sizzle, high bandwidth streams of spectra, particle counts, field maps, raw instrument readings. But even if you encode clever compression and use powerful transmitters, you still have to push that data across light years. A tight beam has to be aimed with extreme precision to hit a receiver on a moving planet, orbiting a star, both of which are moving around the galaxy. On the way, your signal passes through interstellar plasma that can scatter, bend, and flicker the beam. Motion of the ship, tiny pointing errors, and turbulence in the medium all combine to blur and weaken what reaches home. So you can easily end up in a situation where the ship reaches its target, runs its experiments, fills its storage with incredible measurements, and then gets damaged or destroyed by dust, radiation, or mechanical failure before it can send a full dump of that data back. You might get a few bursts of low-resolution telemetry, a partial snapshot, and then silence. From Earth's point of view, the mission becomes a fragment, a handful of signals, and then a question mark. All that risk and all the engineering never quite make it back into your scientific record. Now, add the social time lag. Say your mission lasts 20 years of ship time, but because of the combination of distance and time dilation, 200 years pass on Earth. Every time you send an update, it lands in a world that is 2 centuries ahead of the one that built your ship. The people who designed your instruments, argued over the budget, and watched your launch are gone many generations ago. The language you trained in might sound old-fashioned. The culture, the priorities, all of it has shifted. That means your updates don't arrive as breaking news that changes policy. They arrive as historical documents. Your pictures and measurements are still valuable, but they live in a context where people have moved on to different crises and different goals. You can literally outrun your own relevance. The mission that felt urgent and strategic when it launched ends up filed under long-term Curiosity project by the time its results show up. For the crew, that's a brutal mismatch between what they risked and how it's received. At that point, the real casualty of near lightspeed travel starts to become clear. It's not just hardware, it's not just human life, it's causality in the sense of action and feedback. A functioning civilization relies on a loop: you act, you see what happens, you adjust. With relativistic distances, that loop stretches until it barely exists. You send a ship. Decades or centuries later, you hear what it did. Any response you launch to that new information also arrives decades or centuries after that. You can't coordinate, you can't correct, you can barely even argue about decisions in a meaningful time frame. So yes, you can physically arrive at another star, you can send messages, you can technically keep the story going. But the story arrives so late that it stops being part of your active decision-making. It's like trying to steer your own life by reading history books about yourself, written by people hundreds of years in your future. You're present, but out of sync. And running this kind of mission costs staggering amounts of energy. Every bit of power you use to accelerate the ship, to send beams, to run instruments, ends up as heat somewhere. Your reactors, your transmitters, your life support, all of it dumps waste energy into a closed system that has only one slow way to cool down: radiating into space. If communication delay kills your ability to react in time, the heat problem threatens your ability to run the mission at all, because the universe doesn't give you any easy way to throw that thermal garbage away. You've thrown insane amounts of energy into your ship to get it moving, you've taken hits from dust and radiation, and you've powered drives that make our biggest reactors look like toys. So where does all that energy actually end up? It does not disappear. Most of it turns into the most boring sounding but deadly problem you have on a long mission: heat. And in space, getting rid of heat is one of the hardest things you can do. On Earth, dumping heat is easy. You pump it into air, into water, into the ground. Fans blow, coolant flows, and the environment carries the energy away. But in space, there is no air, no oceans, no breeze. The only way to lose heat is to radiate it away as light, mostly as infrared. The basic rule is simple: the hotter a surface is, the more power it radiates, and it ramps up very fast with temperature. That sounds helpful, but there's a catch. To radiate gigawatts of waste heat, your radiators either have to be absolutely enormous or run so hot that they're glowing like blast furnaces. There is no cheap, compact, cold solution. You pay in size, in temperature, or both. Now look at what your engines are actually doing. Every drive, no matter how advanced, takes some kind of ordered energy and turns it into thrust. None of them are perfect. Fusion reactors, antimatter drives, even hypothetical exotic engines always produce some share of their output as waste heat. Right now on Earth, gigawatt-class nuclear reactors already struggle with cooling. They need big cooling towers, rivers or oceans to dump their waste heat into. At relativistic drive levels, you're not talking about gigawatts. You're talking about power levels many orders of magnitude above that, running for months or years, and you have no river. You have a vacuum and a set of radiators bolted to your hull. So your ship becomes a heat pump dragging energy from your fuel and from the environment, then wrestling constantly to shove the unwanted part of that energy back out into space as infrared. That means huge radiator panels, long booms, or inflatable structures, all carefully angled so they can see cold space without being roasted by your own engine plume. They have to run hot enough that they glow strongly in infrared and may be visible light. They are not optional extras. Without them, your internal temperature creeps up and up until electronics fail and people start to overheat. The problem is, those radiators are almost the worst possible shape from a survival point of view. Big, thin and extended. To radiate effectively, they need a clear line of sight to space, so you can't just tuck them away behind armor. They stick out where they can see the sky, which is exactly where micrometeoroids and dust can hit them. At orbital speeds, a grain of sand can punch holes in delicate surfaces. At relativistic speeds, Those grains hit like artillery rounds. A single impact can shred part of a panel, open leaks if it's fluid-filled, or twist a support boom. You're forced to rely on components that are both critical to your survival and highly vulnerable to the same environment you're trying to survive. Even if you keep the radiators mostly intact, the inside of the ship is never perfectly controlled. Every circuit you run, every motor, every life support pump, every computer, every light, all of it produces some heat. On top of that, the hull and shields constantly absorb energy from radiation, impacts, and internal power systems. That energy has to move through walls, conduits, and coolant loops before it reaches the radiators. Along the way, some of it warms the air and the structures inside. Human bodies have their own comfort window. If your internal environment sits at or above around 80 to 90 degrees Fahrenheit, about 27 to 32 degrees Celsius, for long stretches, people start to suffer. Sleep quality drops, concentration goes down, dehydration, and heat stress creep in. Life support systems have to work harder to pull moisture out of the air and keep oxygen levels safe. If temperatures keep climbing, you move from uncomfortable to dangerous, with risks of heat stroke and long-term health damage. So even small failures in your thermal management system can turn into crew issues fast. Now think about what happens if things go wrong in the worst way, if your radiators get damaged in combat, or by dust impacts, or by simple fatigue. Suddenly your ability to dump heat drops. At the same time, your engines might still be running, your reactors are still hot, and the environment is still feeding you radiation. The internal temperature rises. Maybe at first it's just a few degrees, then more. Metals expand, equipment drifts outside its design temperature. Lubricants break down, superconducting magnets, if you use them, quench and dump huge amounts of stored energy as heat all at once. You're now in a thermal runaway scenario. The hotter your radiators get, the more power they can theoretically throw off, but they also start to glow brighter, making your ship easier to spot from ridiculous distances. You may be forced to throttle down or shut off your main engines just to slow the heating, killing your ability to maneuver or maintain speed. That change in thrust might put you at more risk from dust and radiation, or leave you unable to adjust course away from hazards. A simple heat overload turns into a chain reaction of lost capabilities, and you can't fix this by shrugging it off as a side issue. At relativistic speeds, heat is tied into everything else. High engine power means high waste heat. More shielding and armour mean more mass that can absorb and store heat. Stronger reactors and brighter transmitters mean more thermal load. The environment throws in extra heating through radiation and impacts. Your only exit is through radiators that are fragile and obvious targets. So in the end, heat is not just another problem on a long list. It is the background constraint behind all the others. You can't ignore it, you can't pay it once and be done, and the universe gives you no easy dump for your thermal trash. Every second you are pushing hard near light speed, you are pulling the system closer to the edge of what your cooling can handle. And as bad as that sounds, all of this assumes that the physics involved stays exactly the way we understand it now. But when you start stacking extreme energies, extreme fields, and extreme accelerations in one moving machine, you're also stepping into the territory where quantum fields and vacuum effects might start to matter in ways we haven't fully mapped. And then you're not just fighting known problems, you're poking at unknown ones too. You've already seen how known physics makes light speed travel hostile, but there's another layer that's even more uncomfortable. The stuff we only partly understand. Once you push into extreme accelerations, extreme fields, and extreme energies, you're not just building a ship, you're building a moving high-energy physics experiment. And when you do that, you invite quantum effects that might turn into brand new ways for the universe to say no. Start with something that sounds abstract but hits directly at accelerated motion, the idea of UNRRA radiation. In some interpretations of quantum field theory, if you sit in a rocket that accelerates hard enough for long enough, you don't see empty space the same way someone drifting freely does. Instead, in your accelerating frame, the vacuum looks like it has a temperature. It's as if you're sitting in a warm bath of particles that appear from your perspective, even though an outside observer would still call the vacuum empty. We haven't directly measured this effect in a lab, because the accelerations needed are enormous. far beyond what we can sustain for detectors right now. But the math behind it links together quantum field theory and relativity in a way physicists take seriously. For a normal rocket, the temperature is effectively zero, so nobody cares. For a drive that can push at significant fractions of Earth gravity for months, or create violently changing accelerations, that extra thermal glow could move from a tiny curiosity toward a real radiation source you have to factor into your design. That connects to a deeper fact. The vacuum is not actually empty in quantum theory. Even empty SPET has fields in their lowest energy states, with constant tiny fluctuations. You can think of it this way. There's always a background of virtual particles flickering in and out of existence for extremely short times. Normally, they don't show up as real stuff, but in very extreme conditions, strong fields or sharp accelerations can grab those fluctuations and turn them into real particles. We already have examples of this in theory and in related phenomena. Hawking radiation near black hole horizons, where gravity is so strong that quantum effects start pulling particles out of the vacuum. The Schwinger effect in strong electric fields, where you can, in principle, rip electron-positron pairs out of empty space if the field is intense enough. These are not everyday effects, but they are built into the same quantum field framework that explains a lot of things we've already tested. Now think about what that means if you try to cheat classical limits on propulsion. Say you go beyond normal rockets and start talking about warp drives, massive electromagnetic field structures, artificial gravity gradients, or other exotic concepts that try to bend space-time or push directly on the vacuum. To make any of that work at a useful level, you probably need stupendously strong fields, huge energy densities, or wild stress patterns in space-time itself. Once you crank things up that high, quantum effects that were previously tiny could become large. Your exotic drive might start spitting out extra radiation in the form of particle-antiparticle pairs. It might lose energy to unwanted particle production or vacuum polarization. You'd get new unplanned energy loss channels that eat into your already tight budget. Worse, the particles produced could be high energy enough to damage your own ship, turning your propulsion system into another internal radiation source. And the truth is, we do not fully know all the ways this can go wrong, because we've never built anything that operates in those regimes. Every time particle physicists push collider energies or field strengths, they have to be ready for surprises, new resonance peaks, unexpected decay modes, unstable configurations. That's in controlled machines built on Earth, with tons of shielding, safety systems, and the ability to shut down if something looks off. A relativistic starship with an exotic drive doesn't have that luxury. You're operating at the edge of what your theory predicts, with no backup lab and no easy escape. If there's an instability in the way your fields interact with the vacuum, you might not see it until the system crosses some threshold and dumps energy in a way you didn't design for, or kicks off a cascade of particle production you can't easily stop. A quantum blow-up in this context doesn't just ruin a dataset, it can destroy the ship or render it uninhabitable. So when people talk about fixing light-speed barriers with warp bubbles, shortcuts, or clever field tricks, they're usually stacking classical ideas on top of a quantum foundation we don't fully control at those extremes. Even if the equations say something is barely allowed just on the edge, that doesn't mean it's practically usable. The closer you push your design toward turning space-time and quantum fields into active components of your drive, the more you risk triggering effects that bleed energy away, flood your interior with radiation, or destabilize the configuration altogether. The bottom line is simple. If your plan for lightspeed travel requires your ship to double as a mobile experiment in untested high-energy quantum field regimes, you're betting the mission on the hope that there are no new nope mechanisms waiting out there. History and physics says that's a bad bet. Every time we reach a new energy scale or field strength, we found new phenomena, not fewer. That adds yet another layer of uncertainty on top of everything else. Even if you solve the engineering problems we already know about, you might still be blindsided by physics we haven't met yet. And if you decide to dodge some of the energy pain by using gravity instead, trying to milk speed out of close flybys near massive objects, you step into another unforgiving regime, where relativity, tidal forces, and navigation errors can rip your ship apart long before any engine has a chance to fail. You try to save fuel by stealing speed from gravity, but the closer you push this trick toward light speed, the more it stops feeling like free energy and starts feeling like putting your ship's neck under a cosmic blade. Gravity assists are great at low speed. At relativistic speeds, they can turn into a one-shot test of whether your structure, your navigation, and your luck are all perfect at the same time. Start with the version we actually use today. Probes like Voyager, Cassini, New Horizons, and many others got their extra speed by swinging past planets. They fell into a planet's gravity well, whipped around behind it, and stole a little of the planet's orbital momentum. Speeds here are in the range of tens of thousands of miles per hour, tens of thousands of kilometers per hour. At those speeds, Newtonian gravity works fine, the equations are well tested, and the tidal forces across a small spacecraft are tiny. A gravity assist is just careful orbital mechanics and timing. Now scale the idea up to what you would need for serious interstellar travel. If you want a huge energy boost without burning impossibly large amounts of fuel, you might be tempted to go closer to more massive objects, or to do slingshots when you're already at high speed. Near light speed, gravity does not act like a small correction. The curvature of space-time matters, your trajectory is bent strongly, and general relativity, not simple Newtonian formulas, is in charge. If you pass close to something really massive and compact, like a neutron star or a black hole, the gravitational field changes rapidly with distance. The front of your ship and the back of your ship can be sitting in noticeably different gravity levels at the same time. That difference is what we call tidal force. In the mild version, it just stretches you a bit more in one direction. In the extreme version, it tears objects into long, thin strands. Astronomers literally call this spaghettification, when stars or gas clouds get pulled apart near black holes. For a starship trying to skim close for a maximum gravity assist, those tides aren't just a word in a paper, they are real accelerations acting differently along the length of your hull. Tidal acceleration grows with the mass of the object and with how close you get, and it grows fast as you close in, because it depends on distance in a very steep way. Near a neutron star or black hole, the difference in gravity between your bow and stern can reach levels that are far beyond what any structure or crew can tolerate. From the ship's point of view, that means tension and compression at the same time in different sections. The nose wants to fall faster than the tail. Beams and supports have to carry those differential forces. Internal decks feel strange, with down at one end meaning something slightly different than down at the other end. Even if you design for strong materials, those constantly changing forces can flex and fatigue the ship. And for the crew, your internal organs don't care that it is just a tidal field. They still feel relative accelerations. Blood, fluid, and tissue all experience differential pulls that can damage them if the gradients get too strong. The other problem is navigation. Gravity assists are very sensitive to your incoming trajectory even in the gentle regime we use today. Small changes in angle or speed at arrival can change your exit path a lot. Now move that into a relativistic strong field environment near a compact object. The gravitational field is steep and curved, and your velocity is huge. A tiny error in your approach path, a tiny timing slip, or a small misestimate of the mass or spin of the body you're targeting can throw you from a safe slingshot onto a path that dives you straight in, or slings you out in the wrong direction altogether. And at those speeds, there is no easy mid-course correction. You can't tap the brakes halfway through the maneuver. By the time your instruments confirm you're off by a little bit, you may already be committed to a trajectory you can't escape without absurd amounts of extra thrust that you don't have. The window for corrections shrinks to almost nothing, just like it did for dust and navigation in open space, except now the thing you're trying to avoid is a gravity well that can pull you apart. On top of that, close passes near very massive objects bring back other relativistic side effects. Time dilation ramps up more, so clocks on the ship and clocks far away fall even further out of sync. Light paths bend strongly, so your view of the outside world can distort. If you misinterpret what you see because of lensing or delays, You can make wrong calls at exactly the time when you need the cleanest data. Gravity that you thought would save you propellant is now adding layers of timing and geometry problems that have very little room for error. So the trade is clear. Gravity can give you speed without burning fuel, but it adds its own failure modes. Tidal shearing that can tear at your hull and your crew, extreme time dilation that makes coordination with the outside even harder, trajectory sensitivity so sharp that a tiny error can mean total mission loss. And if you push too close to compact objects, you are hanging your entire ship on our confidence in strong field general relativity and our measurements of that specific object, with almost no margin. In effect, you swapped one brutal constraint for another. You tried to dodge the impossible fuel requirement, and you ended up in a region where gravity's geometry is just as unforgiving as the energy problem you were trying to solve. At that point, the question starts to shift. Instead of asking, how do we hit light speed? A more realistic question becomes, how fast can we go before all of these effects, energy, dust, radiation, time, gravity, and navigation gang up and make the mission more suicidal than useful? And that leads directly to a different answer than science fiction usually gives. Maybe the right way to reach the stars is not to chase light speed at all, but to aim lower, to a band of merely high speeds where the universe is still hostile but not automatically fatal. So after all of this, here's the uncomfortable question. If light speed tries this hard to kill you, does the dream of starflight die with it? Or is the real answer much simpler? You stop trying to go that fast? Here's the twist. You do not have to hit light speed to be relativistic. Speeds like 10 to 20% of light, around 0.1 to 0.2 times light speed, are still insanely fast by human standards. 10% of light is about 18 million miles per hour, around 30 million kilometers per hour. 20% is double that. At those speeds, a trip to a star 40 light years away would take about 200 years in the frame of that star if you cruise at around 20% of light. That's long on a human scale, but it's not infinite. It's in the range of generation ships, frozen embryos, or stored genetics, or purely robotic probes that don't care about centuries. So the picture shifts. Instead of a single crew expecting to fly out, land, and come home for dinner, you think in terms of multi-generation habitats. Or you accept that nobody is coming back at all. Or you remove humans from the vehicle entirely and let machines do the travelling. Suddenly, the target is not get there fast enough to be on the evening news, it's get there at all, with a non-suicidal design. But does slowing down to 0.1 to 0.2 times light speed actually fix anything? Or does it just delay the moment everything fails? The good news is, the physics gets nastier very quickly as you approach light speed, so backing off even a little helps a lot. At 10 or 20% of light speed, the relativistic factor gamma is only slightly above 1, not 10 or 20 or higher. That means kinetic energies are still enormous, but not in the planet killer range for every minor mistake. A dust grain impact is still bad, but it's not instantly equivalent to a small nuke. The radiation from the background and from Starlight is boosted, but not turned into a front-facing death beam of gamma rays. Shielding and navigation are still hard at those speeds, but they shift from almost impossible to brutally difficult engineering problems. You can build thicker armour without automatically turning the ship into an extinction-level projectile. You can design active defences and sensors that actually have more than a microsecond to work. You still need serious radiation shielding and smart routing to avoid the worst dust regions, but the trade-offs are less suicidal. You're managing risk, not fighting a guaranteed killing field. So what kind of missions start to look meaningful in that slower-than-light band? Take robotic probes first. A probe launched at 10% of light speed toward a target 20 light years away gets there in about 200 years in the target frame. It's still a long time, but for a civilization thinking in centuries and millennia, that's acceptable. Add in the light time delay for the data to come back, and you're looking at a few hundred years from launch to full science return, not tens of thousands. That means you can actually plan a long-term exploration program. You launch waves of probes. Some fail, some succeed. The results shape the plans of people centuries later, but still within a continuous cultural memory. It's not, we launched something in the Stone Age and it came back in the Space Age. It's our great-grandchildren will see this payoff. Painful, yes, but not meaningless. Now look at propulsion ideas that could plausibly hit those speeds. You're not inventing magic here, you're pushing hard on physics we already understand. One option people talk about seriously is laser-pushed light sails, where giant laser arrays in your home system push extremely light craft to a fraction of light speed using photon pressure. Projects like Breakthrough Starshot are exploring what it would take to push gram-scale or kilogram-scale probes to significant chunks of light speed this way. Another class of ideas involves nuclear fusion drives using controlled fusion reactions to get far higher exhaust velocities than chemical rockets. If we can ever make practical fusion reactors, the same technology can, in principle, be adapted to drive high-performance spacecraft. You also have advanced ion propulsion and beamed power systems, where your ship carries less fuel and gets energy from external stations. None of these are easy, but they sit in the space of maybe this century or next, not rewrite the laws of physics. So the real cinematic truth is less glamorous than punch it to light speed, but it's a lot more compatible with staying alive. The universe doesn't hate travel, it hates cheating. Light speed is where all the curves turn against you at once. Energy requirements blow up, dust becomes nuclear-scale impactors, radiation fields become lethal spotlights, and time dilation disconnects you from your own timeline. But in the band below that, at 10 to 20% of light speed, you still face danger and harsh trade-offs, yet the numbers stop being purely insane. You still need huge energy, but not star-level energy. You still need shielding, but not several yards thick for every surface. You still fight dust and radiation, but the impacts and doses are in a range where advanced materials, smart routing and layered defenses have a chance. Communication delays are still long, but not so long that missions lose all relevance before their data arrives. So when you look at everything together, the message is simple and a little brutal. Trying to hit light speed turns the universe into your enemy on every front. Accepting merely high but sublight speeds gives you a narrow corridor, where the universe is still harsh but not automatically homicidal. You don't need a ship that flies like a beam of light. You need a ship or a fleet of ships and probes that can grind forward at a fraction of light, withstand centuries of punishment, and still deliver their payloads, their data, or their descendants to another star. In other words, the way we actually explore the galaxy probably won't look like the clean, instant jumps you see in fiction. It will look like slow, heavy, long-haul projects, where success is measured in centuries and victory is not "we broke light speed," but "we arrived and we're still alive." This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.